Greetings, class. This is Dr. York-Hammons. We're looking at information from Chapter 8, Section 3, testing the difference between means. But this time we're looking at dependent samples. Now remember, in 8.1 and 8.2, you did two-sample hypothesis testing with independent samples using the test statistic, the mean of sample 1 minus the mean of sample 2. That's just the differences between the means of the two samples. However, with means of dependent samples, we're going to have to use a different method. So what we're going to do first is find the difference that we're going to call D for each data pair. So it's kind of like a before some sort of treatment and after some sort of treatment. So the D is the data entry for the first sample, and we're going to subtract the corresponding data entry from the second sample. So maybe it's like, I think there was an example about weightlifting. So you have 30, let's make sure you have 30. You have 30 weightlifters, and we see how much they can bench press. Then we go through a specific training method to hopefully to build their muscle strength, and then we test them later and see how much they can bench press. And so the D value would be the difference in how much they could weight lift in the beginning minus how much they could weight lift at the end. So that would be kind of an example of finding a value for D. Now, if you had 30 weightlifters, then you would find those differences and you would take the average, that's D bar, the average or mean of the differences between paired data entries. So we would add up all the differences, one for each person in the treatment, and then divide that by N. Now, there are some conditions, just like there were in 8.2 and 8.1 for the testing we did there. The samples have to be randomly selected. They have to be dependent in this case, or paired, and either they tell you one of two things. Either the populations are normally distributed, or you see that the number of pairs is at least 30 or more. Now, when that condition is met, the sampling distribution for the mean of the differences, D bar, actually ends up being a T distribution. So this T distribution with N minus 1 degrees of freedom, where that's your number, your sample size minus 1, will give you a distribution here. And they talk about the values, what each of the variables are. N is the number of pairs of data. D is the difference between entries in a data pair. Mu subscript D is the hypothesized mean of the differences of paired data in the population. And D bar is the mean of the differences between the paired data entries in the dependent samples. And we just told you that D bar was the sum of D over N. And the standard deviation of those differences can be found by using this particular formula. Now, we're going to work a couple of problems at the end of the exercises where we're actually going to calculate or do a t-test. One of the problems has you actually calculating the standardized test statistic. They don't give you, like here, this one gives you 2 columns of data. In your first couple of homework problems, they don't give you any columns of data. They simply give you D bar, and they give you S sub D and N and mu sub D. They give you the 4 things you need to calculate the standardized test statistics, so you'll do that by hand. And then we will, in order to find the critical values of T, we will do a T calculator with N minus 1 degrees of freedom. So I'm going to move to one of the homework problems that we have to do, and I'm going to pause for just a second and open that back up. Now, I've left these formulas up because we're going to have to calculate the standardized test statistic here in a moment. So it says in exercises 3 through 8, test the claim about the mean of the differences for a population. Let me move this over just a little more so you can see that. Of paired data at the level of significance alpha. Now, here's the important part. Assume the samples are random. That's part 1. And dependent. That's condition number 2. And the populations are normally distributed. That is condition number 3. So since we've met those 3 conditions, we can use this data and test the claim. Now we have to look, we're going to look at number 5, and it says the claim is that mu sub d is less than or equal to 0. Now, since it has an equality statement, then that would be our h sub o. Now, I'm going to see if I can copy this real quick and just do a little copy because it's difficult for me to get some of these symbols, and I will just put that back there. And then, so h sub a will be mu sub d, and let's see if I can just get the mu sub d copied there. And that one, the complement of less than or equal to would be greater than 0. So those are our null and alternative hypothesis. But you have to realize the claim was the null hypothesis. So if mu sub d, if we want to, if we support our claim, we do not want to reject our hypothesis. So let's look at this and see what the things we need to do. First of all, we need to find critical values for t sub 0 using the t calculator in StatCrunch. So I'm going to pull StatCrunch up and we'll look at that. So we have a StatCrunch data table pulled up. I'm going to use the T calculator, so I have to go to Stat, Calculators, and T. Now this one, if we look at our alternative hypothesis, the symbol is greater than. So I need a greater than. Now I know it has the equal, but that's the way it works in StatCrunch, but I have to have the symbol that goes with h sub a, the greater than, so you don't have to worry about the equal to, we just need the greater than. Now I have for alpha is 0.10, so 0.10. I just put my value for alpha there. Now my degrees of freedom is n minus 1. 16 minus 1 would be 15. So that's your degrees of freedom. And when you click compute, you can see this red area, which is your rejection region. And it's everything to the right of 1.341. So my t sub 0 is, I don't know, I know that did a, t sub 0 equal 1.341. Now my rejection region in this case is the same as this red area here to the right of 1.341. So if my t statistic is greater than 1.341, I reject h sub o. So I actually have to run the test now. I've got to go back and create the formula and calculate my standardized test statistic t. And I have to use the formula from the book to do that. So we're back on page 438 with the formula to calculate the standardized test statistic. It says t is equal to, little t is equal to, and I have a numerator and a denominator, but no way to do a fraction here, so I'm going to do parentheses. So this is the numerator coming up. D bar is 6.5 minus mu sub d. Now our claim for mu sub d was that it was 0. That worked out nicely because our numerator is going to be easy to calculate. Then I have to divide that. That's my fraction. Here's my denominator. I have to take s sub d, 9.54, and divide that, and I don't have a square root symbol, so I'm going to do sqrt of 16, and then close that off. That's my, so here's my numerator, there's my denominator. Well, in the numerator, it's just going to be 6.5. Now let's use the calculator to figure out that denominator. It's going to be 9.54. So it's 9.54 divided by, and you have to do the 16 and then the square root so that you get 9.54 divided by the square root of 16, then equal, and you get 2.385. Well, I'm going to clear that, and I'm going to take my 6.5, my numerator, and divide that by 2.385, and I get 2.7253, so 2.725 to 3 decimal places. So you have to ask yourself, is this t-value 2.725 greater than 1.341? And the answer is yes. And when the answer is yes, that says we will reject H sub O. Now, if we're going to reject H sub O, and that's our claim, then what we have here is we have enough evidence at the, let's see, if alpha is 0.10, that's 10% level of significance to reject the claim. So we can reject this claim based on the fact that our standardized test statistic 2.725 is in the rejection region. And remember, the rejection region was anything to the right greater than 1.341. So we did reject. We have enough evidence at the 10% level of significance to reject the claim.